look at some practice questions on divergence theorem here. This is coming from chapter 16.9. Now, first, what we want to do is we want to verify the divergence theorem. That will be true for this vector field on the region E. E as an enclosure. Now, so if you have to review quickly what divergence theorem was, we're looking at the surface integral of f over s. The surface S is in fact equal to triple integral of the divergence div f in that space. So in other words, flux over the surface is equal to the divergence within that space. That's basically what we're talking about in terms of divergence theorem. So now, what we're going to be doing is then we're going to try to, using the divergence theorem, we're going to try to evaluate this one first. And then we will also evaluate the same condition based upon the flux and then see if they're equal to each other or not. So I'm going to erase this one first. So I'm going to try to work on the divergence of f first. Let's try to look at that. Div f. What is that equal to? I'm just going to, there will be del dot f. So that means I'm going to take the derivative of the first one against x. So we get 3. Second one is against y, so we get x. Third one is against z, so we have 2x, which is equal to 3 plus 3x. Now, using that, I'm gonna do 3 plus 3x. Now, in dv, but the space that which we are looking at, enclosure which we are looking at is a unit cube. X goes from 0 through 1, y goes from 0 through 1, and z go through 0 through 1 unit cube. So in fact, if I have to sketch this one, it would have been something like this. Something like that. Hopefully you can imagine that. So now that means if I have to write dx here, and then dy, and then dz, all of them will be numerically bounded, so 0 through 1, 0 through 1, and 0 through 1. And you can easily see that dz that goes from 0 to 1, where I don't have any z component, I mean z as a variable, then we get to realize that that's equal to 1. So as dy also becomes 1 as well. So this one would be simplified to 0 through 1, 3 plus 3x dx. Then we get to realize that this must be equal to 3x plus 3 over 2x squared, where x goes from 0 through 1. Then we get 3 plus 3 over 2, and when you plug in 0, everything becomes 0. So we get 9 over 2 as the answer. All right, but based upon the divergence theorem, we're going to try to find the flux now. So the surface in the front, let me call that as 1. And then I'm just going to go around. Number 2 on the right side. Number 3 is side in the back. Number 4 is a side on this side. Top, I'm going to call that as 5. Bottom, I'm going to call that as 6. So hopefully you can see them. And then we're going to try to find the flux for each surface and then see what happens. So to get, for the first area, we know that x is equal to 1. Then our vector field at the location now becomes simply 3y and then 2z. Now, then when I try to do flux through that particular surface, f dot ds, that's same thing as f dot n, normal function, and ds, normal vector is coming from the surface itself. So in case of 1, we know that normal vector is equal, because it's coming out this way, so we get I in x direction. So now what we end up getting is I is first component for 3. So this one now becomes, when you dot these two, we get, since x equals 1, we have 3 dy dz. And the y goes from 0 through 1. And then a z goes from 0 through 1, which is simply the area here when this is constant. So 3 times the area of the square, which is equal to 1, so our answer becomes 3. That's the flux at the surface number 1. How about surface number 2? Surface number 2 is the one on the right here. That's when y is equal to 1. Since y is equal to 1, then everything stays the same except the middle one. So we get f equals 3x, x, and then xz. Now, in the second surface, the normal vector is equal to what? J. So our integral f dot ds now becomes j, which is this component, only x. So we have x dx dz. X goes from 0 through 1. Z goes from 0 through 1 as well. So when you evaluate this one, you get to realize that that's equal to 1/2. Not bad. Let's look at the third one. Third surface. That's one on the bottom. That's when x equal to 0. So x equal to 0. Then in that case, f now becomes 0, 0, 0. You see, since the vector field is 0, 0, 0, so what we end up getting is f dot ds simply becomes 0. So nothing happens. There's no flux through that surface. Number 4. Number 4 is when y is equal to 0. So y equal to 0, then f becomes, I believe that it is 3x and then 0 and xz. But I believe that it was 2xz. Yeah, 2xz. Now, normal vector would be opposite from 2, where it goes out this way because positive direction outside of the solid. So what we end up getting is we get negative j. But when you dot this, when you dot this one, 3x doesn't have anything, and 0 is multiplied to negative j. So what we end up getting is f dot ds is once again equal to 0. So so far, surface for 3 and 4 becomes 0. Let's look at surface 5. Surface 5 is one, that's 1 on the top. So in that case, z is equal to 1. Then we get f is equal to 3x, and then yx, and then 2x. So then when I, in that case, we get normal vector will be equal to k. So when I do that, f dot ds simply now becomes 2x. X goes from 0 through 1, and then dy goes also from 0 through 1. And as dy goes from 0 through 1, it's equal to 1, and this one also becomes 1 as well. So number 5 is 1. So far we have 3 different values here. How about the last one? Surface 6. That's when z is equal to 0. It's on the bottom, so the function, the vector function now becomes 3x, yx, and then 0. Where normal vector becomes negative k. So when you dot these two, we get 0 as well. So then when you count all the fluxes together, so we get 3. We get 1/2. The other two are equal to 0. We have 1 and then the last one is 0 as well. So when you add up 3 plus 1/2 plus 1, we get, that's right, 9/2. So you can see that it matches. All right, let's look at the next question, number 5. So use the divergence theorem to calculate the surface integral flux right over here across the surface S. So now, based upon the divergence theorem, what I can do is I can figure out divergence of F. In this case now becomes e to the x sine of y. Second one is against y, so then we get negative sine of y e to the x. Thirdly, we're going to take the derivative of this one against z, so we get plus 2yz. Which, since first two terms cancel away, we got 2yz left. And then x, y, z goes from 0 through 1, 0 through 1, 0 through 2 for z. Then we get 0 through 1, 0 through 1, 0 through 2. So we have 2yz dx, dy, dz. Then we can see that 0 through 1 dx, 0 through 1, 2y dy, and then lastly 0 through 2 for z dz. Now you know that first one will get you 1. How about the second one? This will get you 1 as well when you evaluate this one. Third one, on the other hand, is in fact we get z squared over 2, so we get 2. So when I multiply them out, we get 2 as the answer. That's how we can do this question. All right, good job, and I'll see you later. Bye-bye.